Let's move on.
So our very last talk of, I think it's 120 something presentations that have been given over the course of this 4 months in various different venues and formats and whatever. So no pressure. No pressures.
Yeah, just wrap up the whole thing.
And actually, it's particularly fitting that Sarah should be talking this, because actually she was one of the original people who helped put the proposal together that we presented to the INI, and which they happily accepted. So we're extremely grateful to her for that, because without your contribution, we probably wouldn't be here. So thank you for squaring the circle and telling us also about the challenge of cultural engagement with modern history of mathematics.
Thank you. And I mean, what a 4 months, right? It's been so amazing to have been here for parts of that time, and you know, the organisers have been fabulous, and everyone, the Institute's been just amazing. It's a wonderful place to be. So I'm really, really grateful to have been a tiny, tiny part of that. I think we all have just had a brilliant time. So this closing workshop, the formal title of it is Looking Ahead. I'll do my best to think about what, you know, where we might go, and in my sort of particular wheelhouse, which is increasingly communication of mathematics, public communication. And the challenge really is that mathematics is increasingly specialised. So if you just look at a randomly selected research article, even people who are specialists, you know, in a particular research area, may not necessarily be familiar with all of the terminology and notation, even within that small research area. So I'm an algebraist, I'm a group theorist, but within that there's lots of flavours of group theory even. And so if you're doing simple groups, you know, you may be less familiar with the terminology around P groups. And so you look at this kind of thing, and this is just the introductory section of a paper. And I looked at this last night, so I just need a bit of maths to go on the screen. You know, like sometimes when people come and talk to you from a newspaper or something, they say, do some maths on the blackboard, do mathsy things. And you're like, oh, I don't know, what should I do? Anyway, here's some maths. And looking at this, even the authors of the paper themselves might not necessarily. I'm looking at that thinking, what was that? What's that Agamo thing again? That's your upside down home, because I've forgotten what that notation means. So, you know, this is very specialist stuff. And, you know, with mathematics being increasingly specialised, what are the implications for the broader societal conversation around mathematics? And so my focus in recent years has been thinking about the connections between mathematics and literature. And so that's the lens through which I want to talk about these kind of questions today. And, you know, it's more fun than trying to explain what all of those symbols mean in the next hour. So there's lots of mathematical references, metaphors in classic literature, and we'll see some of these. But, you know, here we are in the 21st century. Is it becoming impossible for literature to engage with modern mathematics? Is it just too hard? And in, you know, public communication, which is where I spend a lot of my time, how do mathematicians and historians of mathematics go about telling the stories of mathematics and 20th, 21st century mathematics, especially in a context where, you know, there are a lot of people who don't feel there's any connection between mathematics and culture, whatever that is. So that's a challenge. And, you know, these are very, very big questions, and we can't answer them in an hour. I definitely can't answer them. But all I can do really, and you're very kind to listen, is to offer my perspective as a mathematician who tries to communicate mathematics to the public, and how I try and address some of these things in what I do. And, you know, this programme, Modern History of Mathematics, you can read that the modern can apply to the mathematics or to the way we do history of mathematics. And I guess what I'll say touches on both of those aspects a bit. So when we think about literature and the connections with mathematics, what it can tell us is what was the cultural understanding of mathematics at that time, the time that the literature was being created? How does society view the various aspects of mathematics? There's no point making a cultural reference in your book or your play if literally nobody in the audience is going to understand what you're talking about. So if there is some kind of reference in a book or some piece of literature, we can perhaps think that that means somebody in the desired audience is going to pick up on that. Maybe not everyone, that's fine. So since I decided to call this talk Squaring the Circle, let's go back to what I think, but I'm probably wrong, and someone can tell me. I think this might be the first reference, like a mathematical reference that I can find in a work of literature, but I'm very, very happy to be corrected on this. So Aristophanes in the birds, so they're trying to create this sort of ideal society in the sky, and trying to work out what they're going to do. And at one point, this chap Meton comes onto the stage. So he was a real person. Probably at that time, he would have been most famous for looking at ways to make the calendar work. So it's a very annoying fact, as we all know, that there aren't exactly 365 days in a year, and there aren't a whole number of lunar months in a solar year, and that's very irritating. What Meton noticed was that in 19 tropical years, and so in 19 times that the Earth goes around the sun, there's almost a whole number of lunar months. I wrote down what it was. 235 lunar months is very, very close to 19 years exactly. It's like 2 hours difference in 19 years. So he noticed it. He thought that actually, this is an exact thing, so we can make our calendar be a 19-year cycle, like actually we still do for Easter, right? A 19-year cycle, and then some years will have 12 lunar months, and some will have 13, and it all matches up the cycle. So this is perhaps what he was known for at the time. He wasn't necessarily known for town planning, so he comes on to the stage and he says, right, and he's got these bits of equipment, which he describes as air rulers-ish. For the Greek experts among us, which is not me, you can translate that however you wish, but I think it's roughly air rulers. So he's got these kind of geometric implements that he comes onto the stage with, and people are going to recognise these are the tools of the trade of geometry. And then there's this sort of slight pun because they're trying to build this place in the sky, right? So he says, I'm going to survey the air for you and divide it up into lots. And of course the joke is, survey, I mean that's the same word as geometry, right? Because it's measuring the Earth. So I'm going to measure the Earth, but the air. So already it's a bit ridiculous that he's going to do this. And then he says, so he's got these instruments, he's sort of waving around in the air, and he says, okay, I'm going to place the straight edge, and I've got this circle that I've drawn, and I'm going to square the circle. And so this is funny because he doesn't do this. In fact, what he does is he makes this figure. So he's squared the circle because he's put 4 right angles in it. So job done. And everyone will, in the audience at the time, like, we know squaring the circle is something the geometers are trying to do. We recognise the tools of the geometer's trade, the compass, the straight edge, and we know that this is this is not the question, this is not what squaring the circle means. So fun is being had at his expense. Possibly it's been suggested that this messing about with the calendar might have annoyed people. It's like, oh God, this again, can't they just let us get on with our lives? Now we have to do a new system. But yeah, so he comes on and he squares the circle, but in a comically wrong way. These ideas of classical geometry are a cultural touchstone for 2 millennia. And references to the tools of geometry and geometry itself are very, very frequent. So we just skip forward 1,500, 1,600 years or so. Here's a poem by John Donne, where he's telling his beloved, look, I'm going away, but you're not allowed to be sad because I'm going to come back. And the way he talks about it, he says, look, we have got 2 souls, but they're not really 2, they're really 1. But even if they are 2, then they're like the 2 legs of a compass. And you're the fixed place, the fixed foot, and then I'm moving around, but I'm kind of leaning towards you. I'm always hearkening after coming back, together. John Donne, so there's a bit of sexual innuendo in there because the compass becomes erect. And then so eventually I'll come back, you know. We make a complete circle. I come back to my beginning, and then, you know, eventually we'll be joined together again when the legs of the compass close together. So this is and it's in a love poem. So I'm thinking, you know, nowadays, not as much geometric constructions in love poetry. Maybe there is. Maybe I'm reading the wrong love poetry. There's a line from a Bob Dylan song about the geometry of innocent flesh on the bone, but I don't think he's thinking about ruler and compass constructions. Maybe I'm wrong. Yeah, and we get this compass motif, of course, much more famously in Milton, where he's describing how the universe is being made, and you've got the golden compass, phrase borrowed by Philip Pullman a few centuries later, which is you know, describing the bounds of the earth. And later on, so this is kind of, here is it, the physical act of doing geometry is being used as a metaphor. And then we also get the kind of beautiful edifice metaphor. So later on, Wordsworth, when was this, kind of 1798-ish, not a very good picture of him, but it was the one closest to when this was written. And he's talking about the pleasure that this abstract world of geometry can bring us. The context is, he's talking about, you know, a shipwreck where happily a treatise of geometry was the only thing that survived, and so this you know, person they have a lot of sorrows and miseries because they're shipwrecked, but this treatise of geometry keeps them happy because, you know, you go off and you draw your figures in the sand and you investigate this beautiful, perfect intellectual world, this world that is a clear synthesis built up aloft so gracefully, a world created out of pure intelligence, so it's perfect and lovely. And much later, the same sort of sentiments are expressed here in Edna St. Vincent Millay's lovely poem, Euclid Alone Has Looked on Beauty Bare, where it's you know, this is this perfection. That's what geometry, that's what abstract mathematics can do for us. We forget about all the ridiculous stuff of the real world. And Euclid sees, you know, this shaft of awesome light of inspiration that shows true beauty, and only Euclid has seen that. So this is another kind of motif that geometry gives us in literature, the perfect architecture. So nowadays, right, if you are cultured, whatever that means, you might expect yourself to be familiar with literary references, with Shakespeare's plays, with, I don't know, biblical references, history, music, some sort of whatever we call general knowledge. And, you know, of course, we know that most people don't sit down in an evening and read Shakespeare's plays, but somehow there's this expectation that we have a passing familiarity with these things, and we all know that that isn't the case for mathematics. In fact, it's, at the moment, you know, the knowledge of mathematics, as we all know, is issued. It's like, oh, I was never any good at mathematics. People are okay to say that. Even otherwise very, very well-informed and cultured people. So for me, you know, what progress do we want to make? Even a move away from outright hostility would be an improvement, okay? I'm not saying we have to suddenly all know lots of mathematics, but if we can at least stop being afraid and hostile to mathematics, that would be a start. And so what I try and do is move the dial just a little bit. And in literature, I'll give an example of this. Life of Pi, right? It's there in the title. It's clearly all about Pi. I mean, well, it's about the boy. There's a boy whose name is Pi Patel. He gives himself this nickname because his parents, for reasons best known to themselves, they decided to name him Piscine, like the French for swimming pool. But if you go to school and your name is Piscine, I mean, yeah, it sounds a little bit like something else. So he got a bit fed up of that, and he just goes to school one day and he says, right, from now on, my name is Pi. He draws a circle on the board with the diameter. He writes pi equals 3.14 ... And he says, right, that's who I am now, and I'm Pi. And he says, I take refuge in this Greek letter that looks like a shack with a corrugated tin roof. He literally takes refuge in that letter, in that number, in the elusive, irrational number with which scientists try to understand the universe. And I expect we're all familiar with this, roughly with the story, but the young boy Pi Patel gets shipwrecked at sea, and he spends 227 days floating on the ocean with a large and rather grumpy Bengal tiger named Richard Parker, which that's not the mathematical reference in this book, although if you're familiar with the classification of finite simple groups, you'll know that one of the people involved in it was called Richard Parker, but I don't think that's why. That is not why that name is there. Anyway, I quite like it anyway. So this book talks about Pi, the boy gives himself that nickname, and a read of this book, you know, you see this phrase, irrational number. Pi is a strange, it's sort of paradoxical, because pi is the ratio of the diameter to the circumference. And then what does irrational mean? It means you can't write it as a ratio. So hang on, but you just defined it as a ratio. Okay, let's clarify a ratio of whole numbers. And okay, so we know that pi is irrational, right? Everyone knows that. They don't. 2011, letter to the Guardian. What's the exact fractional value of pi? Not 22/7, which is the commonly accepted approximation, but what's the actual real fraction that they use to work it out to the millionth decimal place? So someone's writing this, and this is not me going, oh, look at this person who's ignorant. This is where we're at. Okay, this is, if you think we don't need to explain this stuff, we do need to explain this stuff. And so not everyone knows that pi is irrational, and not everyone knows what that word irrational means. So when they're reading that book, they miss out on something. We'll come back to, you know, what the use of that word in the book there, because if you don't know what that means, you're missing out on some really cool stuff in the book. And actually, then that got me thinking, so if people don't know pi is irrational, what do they think squaring the circle is? Like, what's that? So I asked a nearby young person in my household, mathematics and households, I grabbed a young person near me, and I said to her, what's squaring the circle? I said, do you know this phrase, squaring the circle? She says, yeah. Okay. I said, well, what is it? What is it? And she said, it means you can't make a circle out of squares. And I said, well, okay, why can't you? Do you know why you can't make a circle out of squares? And she said, duh, it's obvious. Circles have curves. They're like different shapes. I said, no, but okay, but actually the problem is to make a square with the same area as a given circle. And then she's like, oh, well, then obviously you can do it, because just like measure the area of the circle and then make a square with the same area. And I was like, okay, no, right. Okay, but you've got to make it with a straight edge and compass, you know, like you did at school with bisecting angles like that. And then she said, well, that's completely ridiculous. Why would you even, that's like saying, draw a picture of a ship, but you're only allowed to use a daffodil. That was her exact, so then she was like annoyed with this problem. Why would that even be, why try and do something with something that obviously you can't do it with? So that's her understanding. She's not a complete idiot. I am, according to her, but she isn't. So this is the understanding, like, people know it's sort of an impossible thing, but they don't know why, they don't really know what the challenge is or why it's impossible. And of course, it isn't that pi is irrational that makes it impossible, it's that pi is transcendental, but that's another story. Okay, well, why should we care? Why does it matter? Well, it matters if you like literature and if you enjoy, you know, the meanings of things in books. Because the fact that pi is irrational, it's not just that the number pi is mentioned in this book. Its mathematical properties are alluded to in several ways. For instance, I mean, there's sort of a play on words, because Pi, the young boy, he has this time at sea, he recounts this story, and it's got a dreamlike quality to it. We never really know how much is really happening, is something else going on. So there's a sort of play on words about whether the boy, rather than the number, is irrational. But more deeply than that, because pi is irrational, can't be written as a fraction of whole numbers, that means its decimal expansion goes on forever, never repeating in a visible pattern. And so somehow it doesn't end. And Pi Patel says he doesn't like this about his namesake because he hates a bodged farewell. he likes things to have a clean ending. And he says, I wish that my story could have a clean ending, but human stories don't. We have to decide where to start and stop telling them, but it's only ever an approximation. So, that of course, that absolutely ties in with the irrationality of pi. And there's a little treat, actually, in the book, because, yes, we know that Pi's story, the number and the boy, doesn't have a clean ending. However, there's something about the duration of his time on the ocean that's quite interesting. So Jan Martel gave an interview once, and he said that originally it wasn't going to be a tiger, right? That iconic image of this book. It wasn't going to be a tiger that was accompanying Pi. It was going to be a hippo. Which, that doesn't, wow. And he said, I decided it couldn't be a hippo because a hippo is a herbivore and couldn't survive for 227 days at sea. So I had to make it a carnivore. So then, of course, you're instantly thinking, well, that number then is more important than the tiger. It's more important than this thing that we all have in our minds as an image from this book. So why 227? Well, obviously, to me it seems obvious, this is a little nod to 22/7, 227. So he's sort of giving us an almost rational end to this story, and he's making this into an almost rational thing. So it's like a little, we tried, we couldn't absolutely do it because pi goes on forever, but we're almost there. It's an almost rational approximation. So it's a nod to 22/7. And so knowing a tiny little bit of mathematics can really enhance your enjoyment of that wonderful book. So this is why I, think it's great people were to know these things. So from a wonderful, wonderful book, which if you haven't read it, you should, to, and this, life of pi, what about the life of another number, the golden ratio, which there's a lot of, there are lots of things about the golden ratio on the internet. Not all of them are true. I'll just warn you now. There are things on the internet that aren't true, just in case we didn't know. So in the Da Vinci Code, there is a lot of stuff about phi. And I'm going to give you three remarks that particularly entertain me. No mathematician in the history of the world has ever said, as we mathematicians like to say, phi is 1/h of a lot cooler than pi. No. Just no. No. It does not equal, it doesn't equal 1.618. It doesn't. Maybe it doesn't matter that, why does this bother me particularly? Well, it's because Luca Pacioli, in The Divine Proportion, his book about golden ratio, well, in part, one of the reasons he calls it the divine proportion is because it goes on forever. It is unknowable like the divine. So, God does not just have 4 significant figures, guys. This is just not taking away from what the golden ratio even is. So I don't like that. Not equal, approximately equal. And then you've got this gem, because we know the ratio of the terms of the Fibonacci sequence tends to phi. Phi, by the way, as we know, that symbol was not associated to this number until very, very much later than ancient Greek times. Phi was given to it, I think, in the 19th century. Phi is the first letter of the name of Phidias, who designed the Parthenon, probably without any kind of reference to the golden ratio. But anyway, there's this sentence: mathematician Leonardo Fibonacci created this succession of numbers in the 13th century. So again, no, it's true. And look, I know there are people who don't know this, and why wouldn't you think Fibonacci created the Fibonacci sequence? If you learn it in school, it's the Fibonacci sequence. Why wouldn't you think that? We've got to tell people. And the reason we have to tell people is because, as we know, the history of mathematics is not just done by white men in the West, right? And so I mentioned this in my book, that Fibonacci did not invent the Fibonacci sequence. And so this is a bit of advice if you ever do any public engagement. Don't look at the comments. Don't look at the comments online. Some of them will be lovely. And some of them will say, Miss Hart frequently finds cause to denigrate white men. Now, I have just denigrated Dan Brown, so maybe my bad. But okay, so, but these things need to be said. But again, just like people don't necessarily know pi is irrational. People will think that the Fibonacci sequence, it's a natural assumption. And so, okay, this guy who wrote that, I don't believe that I do frequently find cause to denigrate white men, but occasionally I point out that a particular white man didn't invent a particular thing. Hopefully, and I also make mistakes, and that's fine, we all do. We try and be kind to each other. This person probably really genuinely thought that Fibonacci created the Fibonacci sequence. He's just a person, right? But surely a national newspaper wouldn't say that, would they? Well, here's an article from the Times, the paper of record, 2021. Good start. Maths means nothing if we don't know where the numbers come from. Great. It's going to be like, let's learn the history of mathematics. It's so cool. So here's a paragraph from that article. It's published in the Times. I mean, look at the last bit first. We ought to build more monuments to Leonardo of Pisa, because there are not enough monuments to these people. He not only devised the Fibonacci number series, he didn't, which is, trust me, super cool and beautiful. Well, it is. He changed Europe. Okay, so this is, why is the Times publishing this? When you talk to individual people and they happen not to know something, that's completely okay. Like, we're all ignorant about lots of things. And then this part of our job is to try and show people, a bit more of mathematics and a bit more of who's doing the mathematics. But why is the Times publishing this? And even look at that paragraph above. I mean, we could spend the entire, set this as an exercise to students. Name the first 12 misunderstandings in this thing. I mean, so this kind of old thing about when these numbers came in, suddenly people could do mathematics as if they weren't doing mathematics beforehand. Try multiplying using Roman numerals, you can't do it. Yeah, well, that's not what they're for. That isn't. What do you think the word calculation comes from? Calculi, small stone. You have a counting board, you do your calculations. That's why you don't need a zero, because you just leave a gap, right? It's a physical way of doing mathematics. That can be very sophisticated. And then right at the end, you can write the answer using Roman numerals. No one is trying to do multiplication using Roman numerals. So this kind of idea that people were just flailing around, not being able to debt was impossible before Fibonacci, was it? I'm sure I remember reading about how the Roman Senate used to appease the people by transferring all debts incurred in silver into copper, right? So how do this again, it sort of misrepresents what's going on, and the person who's writing this article is, being presented as an expert. So that's a challenge. That's a challenge, right? I'm not a historian of mathematics, right? I like history of maths. I'm a mathematician who does a bit of writing. And so this talk today is me saying thank you to every single historian of mathematics who is working to help us understand the culture, the history of our own subject, so that we can situate it in human history, in human culture. And so I don't originate history of maths research. I'm a conduit, and I'm very grateful for everybody who's done the research to, debunk this kind of story, to understand what was really happening, to situate mathematics in the broader culture, and it really helps. It's fabulous. So yes, please carry on doing it. Everyone who does history is so important. And I just want to give an example of the way in which we can talk about a kind of story that is not this story. The story of, okay, if the Fibonacci sequence was not invented in Italy in 1205, where does it come from? And then we can start to have a discussion about the mathematics that was happening in India for many centuries before this time. And you can talk about the Lilavati, beautiful book of mathematics that has poems that are mathematical problems. And, you know, this idea of mathematicians, yes, can write. They're writing poems, they're lovely poetry, which also contains mathematical questions and problems. And, you know, what a lovely way to do algebra. It's not Bob had 19 watermelons and whatever, you know, it's like, how do I pay my taxes and solve a quadratic equation? It's just these charming, charming poems, nearly 1,000 years ago. And you know, let's tell those stories, which of course historians are doing. Or you can go back a few centuries before that, and you can talk about the fact that, you know, mathematicians clearly are writing in poetry. Of course, if you're a mathematician, whatever you do, you're going to want to do mathematics with it, because that's what we like. So Pingala wrote a treatise, or produced a treatise, and we have to be careful about saying exactly when things happen, because as we know, in this kind of tradition, stuff gets added on, stuff gets attributed to earlier people. So I'm not going to assign any dates to anything, because there are people who are much better at that than I am. But it's ultimately very difficult. But in the analysis of kind of poetic meter in Sanskrit, there are two different kinds of syllables, like stressed and unstressed, just like we have in Western poetry. They're called lagu and guru. Lagu is kind of light and guru is heavy. And so you might ask, if you know, what's my toolbox of poetry? Okay, well, what if I want a meter that contains 4 syllables, let's say? What are my options? How many possibilities are there? And okay, no, with our modern eyes, we say, well, it's, you know, it'll be powers of 2, right? Because there's 2 options for each syllable, so it'll be 16. And Pingala says this. He doesn't obviously talk about binary arithmetic or something, but there would have been two indications. One's for lagu, one's for guru. So this is not him inventing binary arithmetic or binary numbers. But there's something around powers of 2 there that's kind of interesting. And there's even more, you know, and perhaps a little bit later than the original thing, you can be a bit more specific. You can say how many of these things have a certain number of guru, heavy syllables, right? So you're asking how many, you know, 8-syllable lines are there that have exactly 3 heavy syllables. And the instructions say in this book, to work this out, you need to build up like a mountain of numbers. So what that's referring to is, this is a later picture. It's later. I'm not claiming it's 2,000 years old. It's referring to Khayyam's triangle, yes, or that's what they call it in Iran. What we tend to call it here is Pascal's triangle. It arose in thinking about rhythms and meters of poetry and music, because the kth entry on the nth row tells you exactly how many n-syllable meters have k heavy syllables. And there's another question you can ask about this, about poetry. If perhaps you don't want to know about the number of syllables, perhaps you want to know about the duration of that line. And that's different in this form of poetry than in Western poetry. In Western poetry, stressed and unstressed, more or less the same duration, and we say them. But in this poetic form, conventionally, the heavy syllables last longer. They last twice as long. So you sort of linger on them, and that's how you give them the stress. So then, you know, this is sort of me being very anachronistic and putting a sort of notation. But if you want to know how many there are that last a certain length of time, and lagu is 1 and guru is 2, then how do you make one of length n? Well, you can either take an n-1 and add a short lagu to it, or you can take an n-2 length and add a long guru to it. So you get this relationship where the number of ways, you know, dn, the number of duration n, is the number of duration n-1 plus the number of duration n-2, and that is exactly the recurrence relationship that gives you the Fibonacci sequence, so-called. But maybe it should be called the Pingala sequence or something else. So the Fibonacci numbers, they arise very naturally from thinking about the mathematics of poetry. So it's super cool, and that's a really great story to tell that is better than, you know, shopkeepers couldn't tot up their bills until Fibonacci came up. Poor things. So yeah, and so what we can do, you know, knowing the history or a little bit about the history, and I'm not a historian, but you know, the wonderful work of people like Kim Plofka, right? She wrote this wonderful book, Mathematics in India. These are great sources, very important sources. for me to understand and others to understand and be able to tell this kind of story. So thinking about these numbers then, another example of a context helping us to get more out of a piece of literature is, when these numbers are spreading through Europe, which took a long time, actually, they took a long time to reach Britain. We know we're suspicious of European things in Britain, it's very annoying. Shakespeare makes some references to these newish numbers in his plays, because they're weird, right? So he was kind of a generation where his parents perhaps had not been familiar with these numbers, and now his generation was. So they're still relatively a novelty. So this weird thing about 0, that it's nothing on its own, but if you put a 1 in front of it, suddenly it's 10. So it's nothing without a figure, right? And this is what this sort of sneer in King Lear is, you're an O without a figure. You're nothing, because you haven't got a number in front of you. And that's kind of a strange thing, that the meaning of a symbol can change depending on what's around it, which is not as much the case for Roman numerals. Or, there's a nice one here. So this is the beginning of Henry V. So the chorus comes on and says, look, we've got to represent this huge battle. There's only a few of us. You're going to have to use your imaginations, guys. But he says, look, since a crooked figure may attest in little place 1,000,000, let us ciphers to this great account on your imaginary forces work. So the crooked figure, that's a 1, and then the other people on the stage, they can be zeros, right? And that's how that 1 can become 1,000,000, because of these ciphers, these zeros. So he's sort of playing around with this idea of this weird new thing, this 0 that's kind of come into notation in living memory. And so another popularizer of mathematics is Rob Easterwain. He's done a really charming investigation of some of the ways that numbers interact with Shakespeare's work and other mathematical ideas, if you're interested. So that's one thing, contextualizing the mathematical references that we see in literature, but also we can get a little bit more precise here. Sometimes you get a reference that's, certainly for me, so compelling I want to understand where it comes from. This is from Tristram Shandy, right? Lawrence Stern's amazing, crazy, insane autobiography of Tristram Shandy, where he goes off on tangents. Tristram Shandy isn't actually born until like volume 3, right, of this autobiography. So anyway, it's brilliant. If you haven't read it, I'm sure you all have, because you're all very educated people. But there's a point where they're all at Shandy Hall, and Tristram Shandy's Uncle Toby is sort of obsessed with reenacting battles, and he makes these like model battle scenes and reenacts battles. And at some point he's wanting to make a bridge, and the design of this bridge is driving him a bit crazy. So at some point he changed his mind about the bridge design for that of the Marquis d'Hôpital, which the younger Bernoulli has so well and lovely described, as your worship may see, reference to an academic paper in Acta Eruditorum. And then so there's a lead weight that's a balance that keeps watch, blah, blah, blah. Construction was a curved line approximating to a cycloid, if not a cycloid itself. That's all right. If you know me, you'll know that like my special interest is cycloids. I love them. They're brilliant. They're the best things ever. But Uncle Toby struggles with the cycloid. He understood the nature of a parabola as well as any man in England. But he was not quite such a master of the cycloid, and the bridge just never quite happens. So we don't really know cycloids nowadays very much. Like we've heard of parabolas, like we've heard of ellipses and hyperbolas. People have heard of those, and triangles and quadrilaterals. People haven't heard of cycloids. Unless you've done a maths degree, you probably haven't heard of a cycloid. And it's such a simple idea. Just a wheel rolling along a road. Follow a point on the rim. What shape does it make? It's a really cute idea. The name was given to it by Galileo, and I won't give you a whole history of cycloids because you'll never shut me up. But like, everybody was studying the cycloid in, the 17th century. Everyone was studying the cycloid. The statue of Pascal in the Louvre, I don't know how clearly you can see this, but that's a cycloid he's looking at. He said it cured him of the toothache because it's so distractingly lovely. So we should all think about cycloids all the time. There were lots of squabbles around it. People argued about who'd thought of what first. And, in a nutshell, one reason it was so popular and talked a lot about at that time is because it's a brilliant kind of ground on which to try out new techniques of calculus, because some of the problems are involved with things moving along a cycloid and stuff like that. For instance, it's rather later than Tristram Shandy, but there's this lovely reference in Moby Dick to a cycloid. So Ishmael's like hanging around, he's cleaning these big cauldron-like pots called tripods that are sort of all horrible because they rendered down the whale blubber or something in them. And he's doing this, and he sort of has one of his daydreams. He's got the soapstone circling around him, and he realises that in geometry, all bodies gliding along the cycloid will descend from any point in precisely the same time. So that's super cool. It's a reference to the tortichrome problem, just in the middle of the ocean there. Brilliant. So this is one of these problems, the tortichrome problem, posed by Christian Huygens because he wanted to make a better clock. And pendulums aren't quite of constant period, even though we approximate that. So he asked, is there a curve along which a particle can move wherever you start it off from, you know, and wherever you start it off from, it will always reach the bottom in the same time. So this would be like better than a pendulum, or better than a circular arc. And the solution is the cycloid, which is very cool because we encountered it in a completely different place. And a related problem, the Birkbeck problem, which is if you've got 2 points, what's the curve between them, which a particle moving along it will get to the bottom in the quickest time. And weirdly, the solution to that is also the cycloid, which feels like that shouldn't be possible. So I wonder, when I saw this like Tristram Shandy thing, I was like, well, I know that was all a big discussion in ACTA with those people, you know, Bernoullis and L'Hôpitals and those lot were all involved. It's my very dim knowledge of history. I sort of went, oh, yes. I had a look, 1696, and it was posed by Johann, and then lots of people answered it. L'Hôpital, Johann, and Jacob, and Leibniz had this weird anonymous entry to the puzzle, which famously Bernoulli said, famous phrase, right? I know the lion by his claw. He knew that it must have been Newton who had solved this problem and sent in the solution anonymously. So there's this problem that's going around. I thought, but that's got nothing to do with bridges, right? Is Lawrence Stern just making this up? You know, and it sounds plausible. So I got into this and interested, and I found that yes, there really is a paper about bridges. I didn't know a cycloid. I didn't think the cycloid had to do with bridges, so it's a bit confusing. But there is a paper, or several series of papers, in 1695. There's L'Hôpital. There's a problem about bridges, and the problem is, if you've got a bridge that's like A, B there, and then you've got this, I guess, this rope going over from B to C, over like a pulley at C, and down to M, what you want to know is, what curve should the point M move along so that, you know, the rope's sort of pulling it up and down, and it's like a drawbridge, so it's a drawbridge that's going up and down. What curve should this point M move along in order that at all points on that trajectory, it'll be perfectly balanced, basically. So what should that curve be? And this is a question posed by the younger Bernoulli and answered by L'Hôpital. Well, but Bernoulli sort of added a bit to it. He really did it, probably. So then the next bit of the journal has got his response, and he says, I will show that the curve we're looking at, the curve of equilibrium, is the same as that middle of the third line, the cycloid. I could point to it, right? Same as it's identical with a cycloid. But it's actually not what we call a cycloid, this curve. It was then, but it isn't now. So I read a paper about the use of the mention of cycloids in Tristram Shandy by a literary expert, and it wasn't. He didn't realise that what's being talked about is not what we call a cycloid, because if you read the next few words, a cycloid described by rolling a wheel, so far so good, but then over an equal wheel. It's this that is the solution to the problem. We don't call that a cycloid anymore, we call it a cardioid. That name wasn't introduced till the 1740s, cardioid because it looks like a heart, right? So this is a kind of variant cycloid where you're not rolling along a line, you're rolling along a circle. And so I mean, yeah, this might be a little abstruse, but I just find this fascinating that, you know, as we all know, you can see a word you think you know in a text a few hundred years old, and it may well not mean what you think it means. So again, the historians of mathematics can help us with this and tell us what's really going on in these kinds of discussions. And so this is, it says it's about a cycloid, and that is what it was called at the time, but actually now this might have a completely different metaphorical resonance for the book, or maybe it's just that Lawrence Stern happened to be reading this paper and thought it was kind of cool. Who knows? I need a Stern expert. So there are some challenges, right? Here's one challenge. The challenge of balancing clarity with detail and whatever we are pleased to call truth. So yes, if you're writing a popular book or you're giving a popular lecture, you have to miss things out. You cannot tell the whole story of mathematics in one hour or one book or one anything. So what do you miss out? What do you leave in? And those choices, of course, have consequences. You don't want to say anything that's actually, wrong, but sometimes maybe you say number instead of integer, and then you have to decide, is that, how important is that distinction to make? Maybe I'm okay saying number, because if I say integer, half the group won't know what that is. What about truth? So this is something that mathematicians, I certainly have had to learn, because when you, as a mathematician, there's this sort of vibe that, mathematics is objectively true, discuss, but also, okay, the Platonic solids were known 2,000 years ago, and there aren't new Platonic solids now. Like, there've been 5, and there still are 5, and there always will be 5. So somehow that is an eternal truth. Yes, but so we learn that about mathematics, and it means that perhaps you can pick up a mathematics book. I can pick up Burnside's book on group theory from 1897, and it's group theory, and it's not wrong. But if I pick up a book on the history of mathematics from 1897, actually probably quite a lot of it is now not what we would say, because there's new information, there's new scholarship, we know more, we have different outlooks on things, there are different cultural contexts. And so this is something you have to learn if you're a mathematician. And I went through this process. I can't just see something written in a book about the history of maths and just believe it and repeat it. I have to really be sure, and this is, of course, a skill that humanities people learn very early on, and mathematicians perhaps aren't taught that as well as we should be. So, we have to learn this, and the answer there is, let's all be kind to each other and assume good intentions unless we absolutely have proof that there are bad intentions. So that's something to learn for mathematicians, I guess. And that balance of what I will say when I've only got some time and I've got to tell a story. But I want to get it right, and but I can't include every single detail. So what do I leave in? What do I miss out? And to go back to what I said at the start, is modern maths just too hard? Like, are we really going to? We can't have a book that really talks knowledgeably about, I don't know, the Poincaré conjecture, right, or the Riemann hypothesis? Because even to explain what those things are, is it just unrealistic? I mean, and to some extent, perhaps this is an insoluble problem because of the sort of Hubble's law of knowledge, right? That here we are, knowledge is expanding. I don't know when the last person was who knew all the knowledge, but that's a long time ago. And mathematics itself is expanding and becoming more specialised. So yes, to some extent, it is too hard, but there are still things we can do. And books and films and things do talk about mathematical ideas. It does happen. Just 3 random examples. What's Doctor Who doing there? There's an episode of Doctor Who where he meets some aliens and he wants to convince them that he knows his stuff. And so he writes down a proof of Fermat's last theorem. And it's the real proof, like the quick proof. So there's this sort of knowledge that this is this theorem that people have been trying to solve, and that there's supposed to be this short proof. We now have got a proof. Before 1993 to 5, let's say, when Wyles's proof, was achieved, you'd get books where people would find the proof, or you'd get books where it was still an unsolved problem. So I think, there you get science fiction shows where people are still, it's set in the 22nd century and still no one solved it. Well, we can't say that now, but you can still find the short proof. So Fermat's last theorem is just sort of, it's broken through to the popular consciousness. Prime numbers, I don't know if anyone's been watching Prime Target. It's on the Hokum scale, it's quite high, but, it's quite entertaining. So this is all about, finding the secret formula for prime numbers so that you can crack cryptography, right? So prime numbers are sort of known about. Jurassic Park is in there because it's got a mathematician character, Ian Malcolm, played by Jeff Goldblum. Standard levels of charisma, as I say, for a mathematician. And he's a chaos theorist, so there's a bit of discussion of that. And in the book, there are some pictures that are fractals. So fractals is another one that comes up. So there are some ideas that do make their way into the public awareness, and without lots and lots of detail, but maybe that's okay, because does it matter, right? Does it matter if people don't know what mathematicians are doing? Well, in a mercenary way, yes, because we would love it if people would give us jobs and let us do our lovely mathematics. So sort of coming down to the real details of life, we do need to make the case that maths is important. Not all the maths has already been done. Computers can't do all the maths. We do need people. So then what do we want people to know? What do we want to communicate? We're not going to communicate the classification of finite simple groups. What do we want to communicate, and why? And for me, there are three big things, illustrated by three books, or a player book and another book, but I've given you the film poster. So one is, actually, what's it like doing mathematics? It's not just doing hard sums. And that book, Apostolos Doxiadis, Uncle Petros and Goldberg's Conjecture, I read that, gosh, probably 30 years ago, 25 years ago. And it was the first time I'd seen in a book a really believable depiction of what it's like to do mathematical research. Because I remember vividly this description of he's trying to solve Goldberg's Conjecture, he doesn't manage it. Spoiler alert, he doesn't manage it. But he's talking about that when you're really in a problem and you're just fixating on it, you're thinking about it all the time, and then every so often you'll think you might make some progress, or sometimes you think you've made some progress, and then we all do it, like, go away, get some sleep, you'll find the mistake tomorrow in the proof, but for now you need to sleep. And your brain does trick you with this. Like, you can be really, really, and then you just sort of think, okay, it's fine now, and then you have a rest, and then you come back, you're like, okay, that was wrong, but maybe I can now do it, then your brain has rested and you can carry on. So that's a really kind of good description. On the right here, the second thing is, so what's it like doing maths? And the second thing is that mathematicians are people too. Like, we're not all, some of us are insane and absent-minded, but this story, this book, Half of a Yellow Sun, which has got wonderful Chimamanda Ngozi Adichie, the character of Adenibo in that book is a mathematician, but that's not like all of who he is. He's not obsessed with maths and ignoring his family. It's not that. It's not a story about why being a mathematician makes you tormented. He happens to be a mathematician. That's just his job, and he likes it. He talked about it a bit, but it's not all of him. He's a three-dimensional character. I think it's just really important to see that in books. Like, you don't have to be a tortured weirdo. You can be a person and do mathematics. And Adenibo, he's a fully three-dimensional person. He does good things, he does bad things, he's clever and he's stupid in equal measure like all of us. And this is just like, here is a person who happens to be a mathematician. That's important. And then in the middle, the third thing is, maths is so lovely and delightful and a joy, an intellectual joy. And, Tom Stoppard, so wonderful, and Arcadia is double wonderful, and it's got this beautiful depiction of this young woman, Thomasina Coverley, who's just enjoying mathematics, and she has like jokey conversations with her tutor Septimus, talk about Fermat's last theorem, among other things. It's just delightful, and that's what maths is. It's delightful. So those are three messages I think it's so important to send. And we might worry. But, we might say people hate maths and they don't like it. Well, it was ever thus. So sort of, we'll stop in 2 minutes. Longfellow saying, maths is so lovely. Look, it's beautiful. It measures the earth, it weighs the stars, it illumines the universe. It is law, it is order, it is beauty. But then he says, and yet, We imagine, that is most of us, that its highest end and culminating point is bookkeeping by double entry, to mention Luca Pacioli again. It is our way of teaching that makes it so prosaic, like people don't get what maths is all about. This is not like a new thing that people are complaining, that people think maths is big sums. But then what happens next in this book, so this is a quote from a book he wrote, so the character then gets up, goes to bookcase, takes a volume and says to his wife, "Here is a book of mathematics of quite a different stamp from ours. This is how we should be doing mathematics," he's going to say. "Looks very old," she says. "What is it?" "It's Lilavati." And they talk about Lilavati in this book. It's quite charming. So, there is a different way of doing mathematics, and people have been saying that, so let's try and make it happen. But just to finish off with, as we are, I'm in the presence of greatness and these historians of mathematics, I thought I'd give you a historian of mathematics in literature, in their proper place in the pantheon, right? So in this book, Septimania, by Jonathan Levy, there's a historian of mathematics called Mallory. He's studying Newton, he's in Cambridge, and you'll all see that, feel this in yourselves reflected in the greatness of historians of mathematics. In the kingdom of mathematicians, he is a historian of science, bestrode the river Cam with the charisma and stature of a colossus. So you're all incredibly amazing geniuses, and I will finish there. Thank you.
Well, that's a wonderful, wonderful quote, Sarah. Thank you very much. So we do have time for a couple of questions or comments for Sarah. Bridget?
I guess in your challenges, you told us what we want to communicate, and I guess I want to push and hear a bit more about why we want to tell people what it's like doing maths, that we are humans, and kind of why, I think somewhere else, why we want to still be able to convey some mathematical ideas, even if we can't convey the whole thing. So conveying what motivates mathematicians, the tools that they use, that sort of thing. Why do we want to?
Why? God, say why 5 times and then we'll know. I think part of it is just that if, like, the experience of doing mathematics, that kind of enjoyable adventure that you can have is so different from what people experience in school, where it's, not always, and teachers have a really tough job. I love teachers, I'm not complaining about them. But the curriculum in school it's all about, like, maths is useful. It's technology, coding, science, computer, whatever. And it is useful, right? It is. But that's not how we teach art. We don't teach art because it's useful to do technical drawing. We don't teach music because you might write jingles for an ad campaign one day. We teach, it's wonderful and beautiful, and we all sing and we paint and we do stuff. But we don't do that in school. This is obviously I'm not the first person to say it. So I think it's really, for me, part of what I want to communicate to people is that you can enjoy this stuff. Like, it kind of, I don't care that it's useful. I know it's useful. We all know it's useful. Everyone knows it's useful. But I think it might be a bit, that usefulness maybe angle can be a little bit damaging as well, because then obviously you get people saying, well, what will I use this for? Why do I need to be able to prove that the angles of a triangle are at 180 degrees? Why do I care? And then I don't want to have that. That's like not the right question. So I want the question to be, or the experience to be, this is so great. Like, we can work this stuff out. Look at this pattern. We can understand this pattern. Look, there it is over there. So that joy and experience, but also one of the experiences of doing mathematics is of constant failure, right? If you're a research mathematician, you will constantly fail. And then one problem we get is that when people get to sort of a certain stage in mathematics, they'll reach a point where they don't understand something, and the risk is then they just think, I'm no good at maths, and they give up. But that is incorrect. Because I'm all constantly failing, and you may have to fail for weeks, months, years, and maybe you make a bit of progress. But if you think it's all just turn the handle, if you can't do it, then you might give up. So I want, this is important for you to understand. Actually, it can be hard, but it's hard in a good way. It's a challenge. And that challenge itself, the exploration, is part of the joy of it. I don't know if that's really answered you.
Right, well, given we've got 5 seconds left, I think.
4, 3, 2.
Well, very quick, right.
Yes,
Last word to Mike.
Thank you for your talk. I have a question because when you pose the challenge that modern maths since Hart, I discovered in mathematics, there is an area in mathematics, I don't know in my country, is abstract algebra.
Yeah.
We discovered that we have few people doing abstract algebra. And from what we see in the history of mathematics, most mathematics concept came from algebra. So the question I'm asking is it that we in algebra are not teaching it to be interesting? Or why is people not showing interest in group theory and abstract algebra? I don't know.
So, I mean, certainly a lot of things have come from algebra, but algebra itself might be said, has come from other things as well. So there's a whole story. But, to get people, when I talk to people about group theory, which I love, I start by talking about symmetry. Because everyone likes symmetry, right? And then so you can talk about symmetry. And then if you're creating a piece of art or tiling or something, you might want to know how many ways does this thing fit together? What are my options? What are my possibilities? And that's what mathematics can be so good at doing. So I try and contextualize or situate the mathematics behind a question that is natural to ask, like symmetry. Most people agree that symmetry is sort of a good and beautiful thing somehow. And so then we might want to understand it so that we can make more of it. And then actually maths can really help us with that. And you sort of naturally find yourself moving away from, I physically want to make whatever it is, and there are 5 options, to then thinking about, actually we can think about these ideas much more generally, more broadly, and so hopefully, we can at least give a flavour for what a mathematician might try and do and why they might get into it and why they might find it so beautiful. So, yeah, but of course, we need more group theorists. That's
Okay, all right, well, I think we really are out of time, so thank you once again, Sarah, for a really lovely and inspiring talk.